Welcome to the Deep Dive, where we take a topic you're curious about and really explore it, serving as your shortcut to being truly well-informed.
Yeah, helping you get up to speed quickly.
Exactly. So today we're plunging into the fundamental world of chemistry experiments, those hands-on activities that reveal so much about how stuff works.
That's right. We've got a collection of practical activity guides as our sources,
Hmm.
and our aim is to go beyond, simply recalling what you might have done in a lab ages ago.
Right. We want the why.
We're after the core principles at play and those surprising little details that often get overlooked.
Okay, let's unpack what we're diving into. Our sources cover a fantastic range, from finding enzymes in everyday things.
Like potatoes and liver?
Yeah, to understanding water hardness, a neat chemical test for water itself, even creating glass and colored glass.
And tracking reactions by temperature, growing metal crystals with electricity.
Making solids appear through precipitation, the classic acid-alkali titration, exploring ammonia gas, which has a very distinct smell.
Definitely memorable. And finally, figuring out the precise conditions that lead to, well, rust.
So, a lot to cover.
What's fascinating here is how each of these, seemingly basic experiments unveils fundamental chemical principles. Our mission is to extract those key insights and share some genuine aha moments with you.
Okay, let's kick things off with enzymes, those incredible biological catalysts that drive so many processes in living organisms.
That's right. Enzymes, they dramatically accelerate chemical reactions that would otherwise be way too slow to sustain life.
So they speed things up.
Massively. Our first experiments focus on a specific enzyme called catalase.
Catalase, got it. And what's its main role in these experiments?
Catalase's job is to break down hydrogen peroxide, which is actually toxic to cells, into harmless oxygen and water. It's basically a rapid detoxification process.
Okay, so the experiment involves putting hydrogen peroxide in a flask and then adding different sources of this catalase. What everyday materials are we using?
The activity guide suggests liver, potato, and celery, common items, but, each with distinct biological roles.
Definitely. So what should we be looking for when we add these to the hydrogen peroxide? What happens?
The key observation is the production of gas. Bubbles. The catalase present in these materials will kickstart the decomposition of the hydrogen peroxide, releasing oxygen gas.
And how do we confirm that the gas is oxygen, not just, say, carbon dioxide or something?
Time for the reliable glowing splint test, right? Precisely. A glowing splint held in the presence of oxygen will relight, or at least glow much brighter, because oxygen supports combustion.
Okay, here's where it gets really interesting for me. Which of these three, liver, potato, or celery, do you think will be the most effective catalyst? They're all biological, sure, but their functions are so different.
Well, this is where thinking about their biological functions becomes key. Liver, as an organ heavily involved in metabolism and detoxification in animals, is expected to be particularly rich in catalase. It needs to deal with hydrogen peroxide, a byproduct of cellular respiration.
Okay, makes sense. What about the plants?
Potato and celery, being plant tissues, will also contain catalase, but probably in different amounts, tailored to their specific needs.
So it's not just about being biological material.
No. And interestingly, the significantly higher catalase activity often seen in liver compared to potato and celery really highlights this crucial role in animal metabolism.
So we'd expect the liver to produce the most vigorous bubbling, the fastest reaction.
That's a reasonable expectation, yeah.
Yeah.
The rate of gas production, the fizzing, serves as a visual indicator of the enzyme's activity.
And the word equation is pretty straightforward.
Very. Hydrogen peroxide decomposes into water plus oxygen.
Simple yet fundamental. Okay, let's move on to something we all use. Water. But we're not just talking hydration, we're diving into its hardness. And no, that's not about it being ice.
Right. Water hardness refers to the presence of dissolved minerals, primarily compounds of calcium and magnesium. A telltale sign of hard water is that it doesn't lather well with soap. You need more soap to get bubbles.
Right, I've noticed that. And there are different types of hardness.
Exactly. There's temporary hardness, usually caused by dissolved calcium and magnesium bicarbonates. This type can actually be removed by boiling the water.
Boiling gets rid of it. How?
The heat causes these bicarbonates to precipitate out of solution. They form a solid, like the scale you see in kettles.
Ah, okay. And the other type?
That's permanent hardness. It's due to other dissolved salts like sulfates and chlorides. Boiling doesn't remove these, they stay dissolved.
So how do these experiments test for hardness in different water samples? What's the method?
Well, the method involves adding soap solution, drop by drop, to different water samples.
Yeah.
The guide suggests rainwater, seawater, temporary hard water, and then boiled versions of seawater and temporary hard water.
Okay.
And the crucial part is to measure the volume of soap solution you need to add, get a lasting lather, one that sticks around for about 30 seconds even after shaking.
So the more soap needed, the harder the water. That makes sense. The dissolved minerals must be, like, interfering with the soap somehow.
Precisely. The experiment usually includes a table to record these volumes, prompting you to make comparisons. For instance, rainwater. It hasn't really flowed through mineral-rich ground, so would you expect it to be hard or soft?
Probably soft, right? Less chance to pick up minerals.
Good thinking. What about seawater, though, with all those dissolved salts?
Oh, that's gotta be hard. Very hard, I'd imagine.
It really makes you think about the journey water takes. And then there are the boiled samples. Boiling temporary hard water should mean you need less soap afterwards.
Yeah, because you remove the temporary hardness.
Exactly. But with seawater, if it primarily has permanent hardness, boiling might not make much difference in the soap needed.
So the results tell you what kind of hardness is present.
These are precisely the questions the experiment encourages you to investigate. Does seawater contain temporary, permanent, or both? The results table helps you figure that out. The fact that boiling only removes temporary hardness reveals the different chemical forms of these dissolved minerals.
Okay, from the everyday issue of hard water to something that feels a bit like revealing a hidden property, a chemical test for water itself.
Yes, this experiment shows that certain chemicals have a really strong affinity for water molecules, and this leads to a noticeable change in their appearance, usually a color change.
And the key player in this color-changing act is cobalt 2 chloride. Right, I remember that from school.
That's the one. Anhydrous, or dry cobalt chloride, is usually blue, but when it becomes hydrated, meaning it absorbs water molecules, it transforms to pink or purple.
So blue when dry, pink when wet.
Basically, yes. The experiment involves creating a cobalt chloride solution, maybe mixing it with a bit of salt solution, and applying it to filter paper.
Wait, why the salt solution? What does that do?
That's an interesting point raised by the guide. The salt solution, likely sodium chloride, might help ensure a good coating on the paper, or maybe influence how it interacts with moisture. It's a good question to think about.
Okay, so we treat the filter paper with this blue solution, and then what happens?
You observe the color changes. First, as the paper dries, you might gently warm it over a beaker of hot water to speed it up, watching it turn blue. Then you see what happens when the dry blue paper is exposed to humid air, or just breathed on.
And it should turn pink again as it absorbs moisture.
Exactly. It acts like a simple moisture detector.
And the guide asks how many times this color change cycle can occur. Is it a one-time trick?
No, not really. In theory, the cycle could repeat many times as long as the cobalt chloride stays on the paper. Each time it absorbs water, pink. Each time the water evaporates, blue.
That's quite a neat property, and the guide prompts us to think of a practical application. I'm imagining those little indicator strips you sometimes find in packaging to show if something's been kept dry.
Spot on. It's a basic but effective way to detect the presence or absence of moisture. It's crucial to remember the safety note here, though. Cobalt chloride is toxic, so careful handling is essential. No tasting the pretty colors.
Definitely noted. All right, now for something truly transformative, making glass. It almost feels like we're stepping back into an alchemist's lab.
In a way we are. Glass making involves melting a specific mixture of chemicals at very high temperatures and then cooling it rapidly so it solidifies without crystallizing. This experiment uses lead tide, oxide, boric acid, and zinc oxide.
Lead oxide. Okay, that sounds like something needing serious caution.
Absolutely. The safety precautions really emphasize its toxicity and the importance of avoiding inhaling any dust. The mixture is heated intensely, usually in a crucible, until it becomes a molten, runny liquid, like honey, but much hotter.
Wow. And then the transformation happens.
Almost instantly upon cooling, the molten glass is carefully poured or dropped onto a heat-proof surface to solidify into little glass beads or shapes. It's a small-scale demo of a process that's thousands of years old.
But the really captivating part for me is creating colored glass. How does that work?
Indeed. This is done by adding tiny quantities of transition metal oxides to the molten mixture before it cools, things like copper oxide or iron oxide.
Tiny amounts?
Yes. The instructions specifically warn, do not add too much powder or you will produce a very dark piece of glass. It highlights the delicate balance needed to get vibrant colors.
Why do those metals cause color?
It's all about how the electrons in those metal ions interact with light. Different metal ions absorb and transmit different wavelengths of light, which is what we perceive as color.
So what kind of colors might result? You mentioned copper and iron.
Yeah. Different transition metals give characteristic colors. For instance, iron oxides can give greens, browns, maybe yellows. Cobalt oxide typically yields a deep blue glass. Think Bristol blue glass. Chromium can result in greens or yellows too. It's this fascinating blend of chemistry and artistry.
Very cool. Okay, from the intense heat of glass making to the more subtle temperature changes in a chemical reaction. Next up is thermometric titration. That sounds very precise.
It is, well, it's a precise technique. Titration itself is used to find the concentration of a solution by reacting it with another solution. The concentration of.
Right, adding one liquid to another carefully.
Exactly. Thermometric titration adds another layer. You monitor the temperature change during the reaction. Many reactions release heat. They're exothermic.
Like the one we're looking at.
Yes. The reaction here is between hydrochloric acid and sodium hydroxide, a classic acid-alkali neutralization. It releases heat.
Okay.
The endpoint of the reaction, where the acid and alkali have perfectly neutralized each other, is often indicated by the point of maximum temperature reached, the peak heat.
Ah, so the temperature tells you when the reaction is complete.
Essentially, yes. The magnitude of this temperature change also tells you something about the energy released. I see the guide mentions the concentrations of the solutions are different. Why might that be important?
Good question. Using different concentrations can sometimes make the temperature change around that endpoint, the equivalence point, more pronounced, making it easier to pinpoint the exact volume needed for neutralization.
Okay, so the experiment involves adding small, measured volumes of hydrochloric acid to sodium hydroxide in a polystyrene cup. Why polystyrene?
Ugh, good insulator, right. To minimize heat loss to the surroundings, so you measure the heat from the reaction itself.
Makes sense. So you add acid, stir, measure the temperature, add more acid, stir, measure again.
Exactly. You keep doing this, recording the temperature after each addition until you've definitely gone past the point where the temperature reaches its maximum and maybe even starts to drop slightly.
And that highest temperature recorded signifies the end point.
That's the idea. And then we plot these results, volume of acid added versus temperature, to visually identify that peak temperature on a graph.
Precisely. The peak of the curve on the graph shows you the neutralization point. The guide specifically asks for the highest temperature reached and how to draw the graph, linking the practical work to data analysis.
Got it. Now, for something with a bit more visual flair, growing metal crystals using electricity. That sounds like something out of, I don't know, a science project dream.
It's the fascinating world of electrochemistry in action. This experiment demonstrates electrolysis using a tin chloride solution. Electrolysis is basically using electricity to force a chemical reaction to happen that wouldn't normally occur on its own.
Okay, so we have a setup with a steel nail and a carbon rod acting as electrodes connected to a 4V power supply. Which electrode is which? What do they do?
Right. The steel nail is set up as the cathode, that's the negative terminal. The carbon rod is the anode, the positive terminal. When you apply the voltage, current flows through the tin chloride solution.
And the key thing we observe is the formation of tin crystals on the nail, the cathode. Why does it happen there specifically?
Good question. At the cathode, the negative electrode, it attracts the positively charged tin ions that are dissolved in the solution.
Opposites attract.
Exactly. The tin ions arrive at the cathode and gain electrons. That's a process called reduction, and they turn back into solid tin metal atoms. These atoms build up, forming those visible, often quite pretty, crystalline structures.
So electricity is turning dissolved tin back into solid tin.
Precisely. This process is fundamental to industrial applications, like electroplating coating objects with metal and refining metals.
The guide includes some important safety warnings. Avoid inhaling fumes, don't run the electrolysis for too long, and the 2-chloride solution is an irritant. Safety first, always.
Absolutely. Electrolysis can sometimes produce gases at the anode, maybe chlorine gas in this case, and the solutions themselves need careful handling.
The questions related to this experiment push a bit further. It asks what product might form at the other electrode, the carbon anode.
Well, at the anode, oxidation occurs, loss of electrons. Here, it could involve the chloride ions from the solution being oxidized, possibly forming chlorine gas, or maybe the carbon electrode itself reacting.
And it asks us about a common household use for steel electroplated with tin.
Think about tin cans. Food cans are usually steel-coated with a thin layer of tin. The tin protects the steel from corroding and is non-toxic, which is crucial for food.
Right. And finally, it asks for the ionic equation at the cathode, showing that reduction.
That would be SN plus 2 showing the tin ion gaining 2 electrons to become solid tin.
Okay, moving from growing crystals with electricity to making solids appear out of seemingly clear liquids. We're talking about precipitation reactions. It's like a chemical magic trick where you mix two clear solutions and suddenly, poof, a solid forms.
Exactly. Precipitation reactions happen when you mix solutions of two soluble salts and the ions swap partners, so to speak. If one of the new combinations of ions forms a compound that's insoluble in water, it crashes out of solution as a solid. That solid is the precipitate.
Okay, and in this specific experiment, we're mixing magnesium sulfate solution and sodium carbonate solution. Both look like clear water beforehand.
Yep, both are soluble salts, so their solutions are clear. But when you mix them, magnesium ions meet carbonate ions, and they form magnesium carbonate, MgUr, which is insoluble in water, so it appears as a white solid precipitate.
What about the other ions, the sodium and the sulfate?
They form sodium sulfate, NiROS, which is soluble in water, so it just stays dissolved in the solution. They don't really participate in the main event.
Ah, so those are the spectator ions the guide mentions.
Precisely. They're present, but they don't change during the reaction that forms the solid. So the process involves mixing the two solutions, maybe swirling the flask.
And then we need to separate the solid, right, using filtration.
Correct. You pour the mixture through filter paper, the solid magnesium carbonate gets caught on the paper, and the liquid containing the dissolved sodium sulfate and any leftover reactants passes through.
And then you dry the solid collected on the paper.
Exactly. The questions in the guide prompt you to write the word equation. Magnesium sulfate plus sodium carbonate yields magnesium carbonate plus sodium sulfate.
Okay.
Then the formulaic equation. MgSO plus NiOSO plus NiROSOs plus the state symbols for aqueous dissolved and S for solid.
And the ionic equation. That just shows the main players.
Right. It focuses only on the ions that actually combine to form the precipitate. MgC plus TOC, it helps to really see what's chemically changing.
Understanding spectator ions is key there. Okay, now we're back to titration, but this time with a different goal. Creating a specific soluble salt that we can then crystallize. And it's one we all know. Sodium chloride, table salt.
Yes, this experiment nicely combines neutralization and crystallization techniques. You start by titrating sodium hydroxide, which is an alkali, with hydrochloric acid.
To reach that neutralization point again?
Exactly, where they've reacted completely to form sodium chloride and water. It relies on getting the amounts just right.
The guide mentions using methyl orange indicator to find that neutralization point. How did that work again?
Methyl orange is a pH indicator. It changes color depending on whether the solution is acidic or alkaline. In this case, it would be yellow in the alkaline sodium hydroxide, and it turns red or orange as you add acid, and the solution becomes neutral or slightly acidic. That color change signals the endpoint.
Okay, so you find out exactly how much acid you need. But then the next step is to repeat the whole reaction without the indicator. Why bother doing it twice? Why not just use the first mixture?
Well, the indicator itself is a chemical dye. If your goal is to get pure crystals of sodium chloride at the end, you don't want it contaminated with methyl orange.
Right, you wouldn't want orange salt.
Probably not. So you repeat the reaction using the exact volumes you measured out in the first titration, but this time without adding any indicator. This gives you a pure solution of just sodium chloride dissolved in water.
Makes sense. Then comes the crystallization part.
Yes. You gently heat the solution to evaporate some of the water, making it more concentrated. Then you let the remaining water evaporate slowly, perhaps by leaving it in a warm place in a crystallizing dish. As the water leaves, the sodium chloride can no longer stay dissolved, and it forms those characteristic cubic crystals.
And safety-wise, the guide reminds us about eye protection because sodium hydroxide is corrosive.
Very important. The questions here connect back to everyday knowledge asking for the common name, table salt. And they ask for the word equation, sodium hydroxide plus hydrochloric acid, sodium chloride plus water.
And the formula equation?
NaOAAQ plus HELAQ plus HEOHAQ plus HEUR. And that reason for the second, indicator-free reaction, is purely about getting pure salt crystals.
Okay, our penultimate exploration takes us into the very distinct smelling world of ammonia gas. It's a smell that's hard to forget.
It certainly is pungent. This experiment involves generating ammonia gas in AIA by heating a mixture of solid calcium hydroxide and solid ammonium chloride. Good ventilation is absolutely crucial here.
Definitely want the windows open for this one.
Or use a fume hood. Inhaling the gas should be strictly avoided. It's quite irritant.
So we heat this mixture, collect the gas, produce. How do you collect it, actually? Is it denser or less dense than air?
Ammonia is less dense than air, so you typically collect it by upward delivery or displacement of air in an inverted test tube or gas jar.
Okay, got it. And then we perform a series of tests to investigate its properties. What kind of tests are we talking about?
Several revealing ones. First, testing its flammability with a lighted splint. Ammonia gas isn't flammable. It will actually extinguish the flame.
Okay, so not flammable. What else?
Then, we test its effect on damp litmus paper. You'd use damp red litmus paper. Ammonia dissolves in the moisture on the paper, forms ammonium hydroxide, which is alkaline, and turns the damp red litmus paper blue.
The classic test for an alkali. What about universal indicator paper? Also damp.
Yes, damp universal indicator paper gives a broader idea of the pH. With ammonia, you'd expect to see a color change towards the blue or purple end of the spectrum, confirming it's alkaline or basic.
There's also a slightly unusual test mentioned, bringing a stopper from a concentrated hydrochloric acid bottle near the ammonia gas. What happens there?
Ah, that's quite dramatic. Ammonia gas reacts instantly with hydrogen chloride gas, HCl, which evaporates from the concentrated acid to form dense white fumes or smoke. This smoke is actually tiny solid particles of ammonium chloride, NH2O.
So it shows a reaction with an acid gas.
Exactly. It demonstrates the basic nature of ammonia very visually.
And finally, the visually striking fountain experiment. That always looked impressive in textbooks. How does that work?
The fountain experiment is brilliant for showing ammonia's extremely high solubility in water. You fill a flask with dry ammonia gas, seal it, and invert it so its opening is underwater, often water containing an indicator like phenolphthalein.
Okay.
Then you introduce just a tiny drop of water into the flask. The ammonia gas dissolves incredibly rapidly into that drop of water. This causes a massive pressure drop inside the flask, a partial vacuum.
Because the gas is vanishing into the water.
Precisely. The much higher atmospheric pressure outside then forces the water from the trough forcefully up into the flask, creating a fountain effect. And as the water rushes in, the indicator changes color. Phenolphthalein turns pink, showing the resulting solution is alkaline.
Wow, that really demonstrates the solubility.
It really does. The guide provides a fill-in-the-blanks question to summarize ammonia's key properties based on all these tests and asks for word equations related to its production.
So consolidates the learning. Colorless gas, pungent smell, not flammable, less dense than air, alkaline, very soluble, reacts with acids.
That's the summary. The word equation for its production here is ammonium chloride plus calcium hydroxide, calcium chloride plus water plus ammonia.
Right. Finally, we arrive at a phenomenon we've all definitely encountered. The rusting of iron or steel. It seems so simple, so common, but I bet there's more chemistry to it than just leaving your bike out in the rain.
You're absolutely right. Rusting, or corrosion of iron, is actually quite a complex electrochemical process. This experiment is designed to pin down the specific conditions that are necessary for rust to form.
Okay, so how does it do that?
3 test tubes are set up, each containing a clean iron nail but under different conditions. It's all about controlling the variables.
Let's break down the setups. Tube 1.
Tube 1 just has the nail with a small amount of deionized water. So the nail is exposed to both water and the air above it, which contains oxygen.
Okay, water and air. Tube 2.
Tube 2 has a nail with deionized water that has been boiled first, and then a layer of oil is carefully added on top of the water.
Why boil the water and add oil?
Boiling removes dissolved gases, including oxygen, from the water. The oil layer then acts as a barrier to prevent oxygen from the air dissolving back into the water. So this tube essentially has the nail in water, but with very little oxygen.
Clever. And tube 3?
Tube 3 contains a nail along with some anhydrous calcium chloride granules, and the tube is sealed with a bung or stopper.
Anhydrous calcium chloride. That's a drying agent, isn't it?
Exactly. It absorbs any moisture present in the air inside the tube. So this tube has the nail exposed to air, oxygen, but in a very dry environment.
So we've got water and air, water but no air, air but no water, approximately.
That's the idea. Then you leave these setups undisturbed for several days, the guide says more than 3 days, and carefully observe the nails.
And what are we expecting to see? What should we record?
The table in the guide is for recording observations. You would most likely observe significant rust formation only in the first tube, where the nail is exposed to both water and oxygen.
What about the other two?
In the second tube, boiled water plus oil, you'd expect to see very little or no rust, highlighting the need for oxygen. In the third tube, with the drying agent, the nail should also remain largely rust-free, showing the importance of water.
So this experiment strongly suggests that both water and oxygen are essential for rust to form. You need the two together.
Precisely. The guide specifically asks why the water is boiled and oil added in tube 2. It's to eliminate dissolved oxygen and prevent its return. Therefore, the key conclusion is that rust requires the simultaneous presence of both water and oxygen.
It's not enough for it just to be wet or just exposed to air.
Correct. The final question prompts you to suggest another method for preventing rust based on this understanding.
Well, if it needs air and water, you could try to block them out, like painting the iron or coating it in oil or grease.
Exactly. Applying a protective coating, like paint, plastic, oil, or grease, acts as a physical barrier. Another common method is galvanizing coating the iron or steel with zinc. Zinc is more reactive than iron, so it corrodes preferentially, sacrificing itself to protect the iron.
Wow, okay. We've journeyed through quite a landscape of chemistry today, from, the microscopic world of enzyme activity right up to the very visible macroscopic phenomenon of rust.
It's truly remarkable how these, on the surface, straightforward experiments illuminate such fundamental chemical principles that literally govern the world around us.
Yeah, what's really captivating is that even familiar things, like a potato fizzing in hydrogen peroxide or seeing limescale in your kettle, are underpinned by these intricate chemical interactions.
Absolutely. The varying catalytic efficiencies of liver versus potato, the subtle differences between temporary and permanent water hardness, that cool color-changing trick of cobalt chloride.
The way tiny amounts of metal make colored glass, seeing a reaction's endpoint just by watching the thermometer.
Right? Or growing metal crystals with electricity, making solids appear from clear liquids, getting the balance of acids and alkalis just right.
The unique properties of ammonia, and figuring out exactly what makes something as common as rust actually happen. Each one tells a really compelling story about how matter behaves.
It really does. Chemistry is happening everywhere.
So as we consider all these reactions and processes, it really makes you wonder, doesn't it? What other seemingly ordinary things we encounter in our daily lives might have surprisingly complex chemical explanations humming away just beneath the surface?
It definitely encourages you to look at the world with perhaps a bit more chemical curiosity.